right, so as far as the exam one review, the only request I got was for like a chance to go over exact equations. So um, let's see, I'm gonna like go through an example, but just in general, I think that having like this roadmap for how to solve this type of problem is good, like right next to you when you're trying to do it. But what I'm going to do is I'm going to go through this like from start to finish as if I was working through it like on an exam so that you can see how it works. And then I'll just remind us as we go how it connects to those steps I told you to follow. So first thing for this is that it doesn't actually look like an exact equation. We always had that exact equations looked like this. This was how we knew like the form so that we knew what m and n were, so we knew what things to check derivatives of. So first I just have to rearrange my differential equation. I take this dy dx right here and I just sort of quote multiply through by dx to separate it so that I'm just left with my 2y plus x squared plus 1 times dy right here. And then dx is multiplied by everything, but the only place where it isn't canceled out is times that 2xy minus 9x squared. And so using that notation we had before, I am pretty sure we called m the thing that you multiply by dx. Yep. So using that notation, we've got that this is our m of xy, and this is our n of xy right here. And for exact equations, the first thing we check is that our mixed derivatives are correct. So we take the derivative of m with respect to x, that partial derivative where we just pretend y is a constant. I just apparently have to write that x over entirely. Sorry, with respect to y, because this is the thing related to x. So we treat x like a constant. So we've got 2xy, just 2x, minus 9x squared is 0. And then we take the partial derivative of n with respect to x, the thing that's attached to dy, take the derivative with respect to x, pretend y is a constant. So our 2y becomes 0, our x squared becomes 2x, and our 1 becomes 0. So we verified that these two things are equal. Which means this is an exact equation. If it wasn't exact, this would be the part where you go on to find that integrating factor by taking the difference between m sub y and n sub x, but we don't have to do that for this example. Instead, what we're going to do is we'll try to find our f of xy, which would be the integral of m with respect to x. So it's the integral of 2xy minus 9x squared with respect to x, which is just x squared y minus 3x cubed plus some constant with respect to x or a function with respect to y. X squared y minus 3x cubed. Okay. Sorry, I just want to copy that down real quick. X squared y minus 3x cubed plus g of y. All right, so our end goal is to find this f equal to c, which tells us a relationship between x and the solution y. We know that it's the integral of m with respect to x, the thing that's attached to dx. And we can compute that integral except there's this unknown g. And so this is the part where things start to get a little bit complicated. So we say, okay, I need to know what g of y is if I want to know what f is. But what I can say is that f minus x squared y minus 3x cubed is the same as g, because that's how g was defined right above. And then I can say, well, if that's what g is, I certainly could find its derivative. G prime of y would be the derivative of f with respect to y minus the derivative of this thing with respect to y. So that's just, let's see, x squared minus 3x cubed is minus 0. And then importantly, if we find f by integrating this with respect to x, or this with respect to y, then when I want to find the derivative of f with respect to y, I just plug this thing in. Remember, f is related to this differential equation, so df dy is here, df dx is here. So I can just plug in what we called n before. And so that's why we always said it's n minus d dy of the integral of m with respect to x. That's sort of that formula that we would have. And our n was 2y plus x squared plus 1 minus that x squared. So it's just 2y plus 1. And then if that's g prime of y, then g of y is the integral of g prime of y. So that's just going to be, see, the integral of 2y plus 1 with respect to y is y squared plus y plus a constant if you are going to be really careful about this. You don't have to, it'll go away. But I'm going to put it there just for the fun of it. So f, now that I know what g is x squared y minus 3x cubed plus y squared plus y plus that constant. But I don't want to know what f is, I want to know what y is. And so when f is equal to any constant, you can find y. So you would take x squared y minus 3x cubed plus y squared plus y plus c1 equal to some constant. And that's why this constant right here doesn't matter, because we set it equal to an unknown constant anyhow, and they'll just sort of cancel out together. So in general, I'll just skip that. As long as you remember to do this thing in the end, you'll be okay. If you had written that plus C1, you just have to remember to combine those constants, because you can only have one unknown constant for a first order differential equation. If you have too many constants, you won't be able to solve an initial value problem. So that's the general solution in implicit form of our differential equation. And we had an initial value problem, so there's an extra step we have to go to here. We have to deal with our initial value. But let me write down that on this slide right here, x squared y minus 3x cubed plus 3x cubed plus y squared plus y is equal to a constant, with y of 0 equal to, I think, minus 3. So here's our general solution, something that has x's and y's and an unknown constant. Here's our initial condition. We just combine those things to try and solve for our unknown constant. So x should be 0 and y should be minus 3. So I've got 0 squared times minus 3 minus 3 times minus 3 cubed plus, oh, look at me, I'm already making mistakes. Minus 3 times 0 cubed, plug in 0 for x, plus minus 3 squared plus minus 3 is equal to a constant. And let's just check to make sure I did all that right. See, I had x there, x there, x there, x there, and then my y's were here, here, and here. And I've got that minus 3 squared, and minus 3. So we're good. Let's see, zeros cancel out there. So I've just got 9 minus 3 is C, is 6. So the solution is x squared y minus 3x cubed plus y squared plus y is equal to 6. And yeah, I'm making these a little bit longer than a regular video because it's like a choice to watch. So I'll go ahead and try to solve this all the way. So this is an implicit solution. It technically tells you how x and y are related. It's good enough. But if that's not very satisfying to you, then what we've got here is a quadratic formula for y. So all I'm doing is rearranging this so it looks like you expect a quadratic to look like. So y squared plus x squared plus 1 times y plus a constant equal to 0. And then to just solve for this, you could use your y as minus b plus or minus square root b squared minus 4ac over 2a. So see, here's our b. So minus x squared plus 1 plus or minus the square root x squared plus 1 squared minus 4 times 1 times negative 3x cubed minus 6 all over 2 times 1. So that's minus x squared plus 1 plus minus the square root of x to the 4th plus 2x squared plus 1 plus 12x cubed minus 4 times minus 3 is plus 12 plus 24 all over 2, which is, if that simplifies in a nice way, I don't know it. So we're just going to leave it under the radical, but at least put it in order. X to the 4th plus 12x cubed plus 2x squared plus 25 all over 2. That would be the solution for y. That box was bad. Sorry. Now it doesn't look like that 2 is part of it. Okay, so that's the solution for y. If you had this problem on an exam, definitely just stop here. That's also a solution for y. Both are acceptable. Just sometimes you all like to have like y equals stuff, and this would be how you do it. So hopefully that helped to kind of see where the exact equation stuff is coming from. Yeah, if you go back to the steps, I know that they look kind of intimidating, like this n minus d dy of integral m dx, and then integral of that whole thing. But when we do the example, hopefully you can see that, you know, that n minus d dy integral m dx is actually just 2y plus 1. So if you plug everything in as you go, the integrals aren't so messy as those steps with those like quote formulas looked. So just go through it step by step, I would say, and do your integrals as you move forward.